Welcome back to SP Gubbi online classes for SSLC and Cbse 10th standard for mathematics and science classes. So in the last session of physics, we had come across the power of the lens, the magnification of the lens, along with sign convections with the important concepts connected to the magnification, that is the relation between U, V and F, that is called the lens formula. So 1 by minus 1 by U plus 1 by V is equal to 1 by F, that was the lens formula. And regarding sign convections, so whatever the measurement you do, that measurement should be taken from the optic center of the lens. So okay, that is the first thing. Second thing is, when you measure the object distance from the optic center of the lens, that should be taken as negative because you are measuring opposite to that of the incident light rays. The image distance will be positive if it is real and inverted, because as you are measuring that distance along the direction of the incident light rays, and the height or size of the object is always, as it is kept above the principal axis, therefore it is taken as positive. And the image, if it is real and inverted, it will be below the principal axis, therefore the height or size of the image is taken as negative. If the image is a virtual and erect image, it will be above the principal axis, therefore the size or height of the image is taken as positive again. So these are the sign convention for lenses. So along with that, we came out with the magnification. It was a very important concept which we had discussed in the previous session. So magnification of a lens is defined as the ratio between the height or size of the image to the size, the height or size of the object. So that is called magnification of a lens. So magnification is defined as m is equal to h dash by h. So that's the mathematical form. So when we came out with the relation between m, u and v, yesterday we had a very simple derivation where I took the help of the concept of similarity of triangles and I showed you the relation between m, u and v. So and at the end of the derivation we came out with a beautiful mathematical form, that is m is equal to v by u. So overall the mathematical form is m is equal to h dash by h is equal to v by u, or h dash by h is equal to v by u, or m is equal to v by u. So any mathematical form you can use wherever required in numericals. So in today's concept we are going with a very important topic on lenses, that is called the power of a lens. So here 100% in most of the examination in the previous year's science papers, what I have seen, they will ask you a question on power of a lens and a small numericals connected to the power of a lens. One more question you have to answer for this, right? So what is power of a lens? So here power of a lens is defined as the ability of a lens. It's the ability of a lens to converge or diverge the light rays which are falling on the lens parallel to the principal axis. So you can imagine what I am telling you. Just imagine a convex lens. This is the principal axis, this is the convex lens. The light rays are traveling parallel to the principal axis, falling on the lens. After getting refraction, they are getting, that is, converged at a point. They are falling on a point on the principal axis. The light rays are converged and fall on a point on the principal axis. So here the ability of a lens, which whatever the lens may be, whether it is a convex lens or a concave lens, whatever lens may be, right, the ability of a lens to converge or to diverge. Converging happens in convex lenses and diverging happens in concave lenses. So therefore the ability of a lens to converge the light rays or to diverge the light rays which are falling on the lens, which are traveling, the light rays which are traveling parallel to the principal axis, is called the power of a lens. So this is the general definition for the power of a lens. So once again I will define this. The power of a lens is defined as the ability of a lens to converge or diverge the light rays which are falling on it. So this is the power of a lens. So here power of a lens is indicated by a letter, that is P. We are going to represent the power of a lens by the letter P, right? So here, how to define this? So this is the general definition what I gave you. Generally when somebody asks you, hey, what is power of a lens? Sir, power of a lens is nothing but the ability of a lens to converge or divert the light rays which are falling on it. It's called the power of a lens, represented by the letter P. That's a general talk about power of a lens. But how to define that? So here, power of a lens can be defined as the reciprocal of the focal length of the lens. This is the definition for power of a lens. So what is power of a lens? So you can, I hope in your syllabus you can write both the definitions. Both are correct and you can get the marks for that. So what is power of a lens? Power of a lens is defined as the reciprocal of the focal length of the respective lens. It is whether it is convex lens or a concave lens, whichever it is, power of a lens is defined as the reciprocal of the focal length of the lens. So this can be defined as power of lens. Power of lens is equal to reciprocal of 1 by focal length of lens. This is the mathematical, write the mathematical form. So power of lens is written as P and 1 by focal length is written as F. So this is the formula for the power of a lens when the focal length is in meters. And the focal length is given in meters. So power of a lens is also defined as 100 by F when the focal length is given in centimeters. So these are the two formulas to measure the power of a lens. So power of a lens is defined as the reciprocal of the focal length of the lens. Very simple. So if the focal length of the lens is in meters, then the formula is P is equal to 1 by F. If the focal length of the lens is in centimeters, then the formula is P is equal to 100 by F. Right? So now let us little bit go depth into the power of a lens concept. Right? So very important. So here, as I told you earlier, the ability of a lens to converge or diverge the light rays which are falling on it is called the power of a lens. So as per my words, we will go in depth regarding the power of the lens. So now, for example, I have a convex lens. Very simple, I have a convex lens. This is the principal axis, this is the optic center represented by O. I have kept an object here, somewhere here. So, when you bring the object very near to the, that is, when near to the lens, real and inverted image is formed. So, when the image is formed at this point, so we take one light ray starting from point A, okay, let us take this point A parallel to the principal axis. It gets refracted and passes through the principal focus. Another light ray are going to take it from the optic center, and these two light rays, maybe I will write here, they are going to meet at some point here, at some point, that is A dash and B dash. So, this is what happens when our light rays are going to fall on a lens. So here, if the lens is having the capability or ability to converge the light rays which are falling on it very, very near to the principal focus. Very, very near to the principal focus. I hope you can understand this. If the power of the lens, power of a convex lens can be defined like this. It can be imagined like this. If light rays are falling on a convex lens which are parallel to the principal axis, they get refracted, and after refraction they are going to meet at a point on the principal axis. And if that point on the principal axis is very near to the, that is principal focus. If it is very near to the principal focus, then we say that the lens has a greater power. A greater power. Right? So in that lenses, we say that the focal length is less. Focal length is less. See, you have to understand the relationship here. I am speaking about the image formation, I am speaking about the focal length, I am speaking about the converging light rays. Three things I am speaking here. So, for example, we will take. So, this is a lens, this is the principal axis. The light rays coming from the, which are parallel to the principal axis, are falling on the lens and they are getting refracted. So, this is, maybe this is the principal focus. So these light rays are meeting at this point. They meet at this point. So which is very near to the principal focus. That is, this lens is able to converge these light rays so effectively that these light rays are falling very near to the principal focus. That is, very near to the principal focus point. So therefore, this lens is said to be more powerful because this lens has lesser focal length. So that if you measure the focal length here, it has lesser focal length. Focal length is very less. So therefore, next case, another lens I will take. So in this lens, the light rays are traveling parallel to the principal axis. Okay, these light rays after refraction, they meet at a point that is principal focus. So here, if you measure this distance, we say that the focal length is more. So here, this focal length is more. That is, it has a greater focal length. Therefore, the convergence of this lens is bigger. That is, it is forming an image very far away from the optic center. But here, when you see here, the image is formed very near to the optic center because the focal length is very less. So, very simple. Okay, this is the principal focus. The light rays falling on the lens, they are falling on a point on the principal axis, that is called the principal focus. Here also, the light rays after getting refracted, they are falling on a point on the principal axis, that is the principal focus. But here, if you measure the focal length, the light rays are converging more effectively, and it is near, the image is formed very near to the optic center, but here the image is formed very far away from the optic center. So here, image is formed near the optic center because the focal length is less. Therefore, we say that this lens has more power. So here, when we speak regarding this, focal length is more. The light rays are converging at a point which is away from the optic center, stays a little bit far away from the optic center. So therefore, this focal length is more. Therefore, we say the power of the lens is less. So very simple. So P is proportional to, that is P is inversely proportional to 1 by F. This shows that more the focal length, that is inversely proportional, I am speaking here, more the power of the lens, less the focal length. So this is how we have to remember this. More the focal length of the lens, less that is the focal length, less the power of the lens, more the focal length. See, this is how we have to remember, because power of the lens and focal length are always inversely proportional. So, if a lens is able to converge all the light rays at a point very near to the optic center, then the ability of this lens to converge the light rays is more. So here, this lens is able to converge the light rays a little bit far away from the optic center. So this is the optic center. A little away from the optic center, the light rays are getting converged. So therefore, here we say that the power of the lens is less. So more the power, less the focal length. More the power, we should understand like this. More the power of the lens, less the focal length. So therefore, right, the distance between, that is the image and the optic center, is less. That is focal length. That is nothing but focal length. So this lens has more converging capacity. So in other words, if the power of the lens is very less, then we have to consider that lens has higher focal length. That has it has a larger focal length. So more the power, less the focal length, less the power, more the focal length. So the converging capacities or the diverging capacities of the lens goes on changing from one lens to another lens. So therefore, power of the lens entirely depends upon the focal length of the lens. So more the focal length, less the power, less the focal length, more the power. This is how we have to remember this concept, right? So how to measure this? Because power, just I cannot say you the power of this lens is that, power of this lens is this. We need a unit to measure the power of a lens. So here, the power of a lens is measured by a unit called diopter. The unit for measuring the power of a lens is called as the diopter, which is represented by the letter D. So what is one diopter. So what is one diopter? So when we speak about unit things in physics, what is 1 Newton, what is 1 joule, what is 1 volt, what is 1 ohm, what is 1 ampere, what is 1 coulomb, something like that. So here also we speak about what is 1 diopter. So the power of the lens is said to be 1 diopter if the focal length of the lens is 1 meter. You have to remember this. If the focal length of some lens is 1 meter, then we say that the power of the lens is 1 diopter. This is very, very important. Define 1 diopter. They will ask you in the examination. So 1 diopter of a lens is the power of a lens whose focal length is 1 meter. Right. So this is 1 diopter. Right. So here we will go with the next concept, that is regarding the uses of lenses. In the previous session we had discussed the uses of lenses also along with ray diagrams. So regarding the convex lenses, I had discussed some 6 uses with you. So among them, convex lenses are used in astronomical telescope. So it's a scientific instrument. So it's an optical instrument which works on light. So therefore, convex lenses are used in making astronomical telescopes used to watch heavenly objects like planets, our moon, stars, something like that. So next is a terrestrial telescope. Terrestrial telescope is also a type of telescope used to see the distant objects on the surface of the earth. Just I want to see something which is very far away from me on earth itself, then it is called a terrestrial telescope. Okay, so they are also used in making microscope to see those minute objects where human eyes cannot see that. So they are also used in making microscopes. They are used in making searchlights, very important. So which are used by some forest officials during night time, or maybe some security personnel, they use searchlights. Maybe in prisons they have very big searchlights. Right. Okay. Anyway, so then they are used in cinema projectors. So usually we will be projecting certain things for you on the screen. So those projectors have convex lenses in them. So they are also used as magnifying glasses. Magnifying glasses in the sense they are used as reading glasses. So reading glasses also made up of convex lens. So then they are also used in treating a defect of the human eye, that is called as hypermetropia or long-sightedness. So that's one of the defect of the human eye. To correct that, they are going to use convex lenses. So apart from that, when we come to concave lenses, concave lenses are used in correcting one of the defect of the human eye, that is called myopia or short-sightedness. Very important. So these are the uses of lenses. So many uses are there for convex lenses. So one use is there for concave lenses. So concave lenses are used to correct one of the human defects, the human eye defects, that is myopia or short-sightedness. So these are the uses of lenses. So at the end of the session, I am going with a very important note for you, which I have observed in the previous year's question papers. So I will discuss a question with you regarding this. Okay, now let us take a convex lens. Very simple. So this is the optic center, this is the f1, this is f2, that is 2f1, this is f2, and this is 2f2. So this is what we have learned. So I will the light rays which are falling on this lens parallel to the principal axis, they are going to, that is, converge at a point on the principal axis after refraction. So we know this is how it happens. Okay. So this is the principal focus, that is f2. What we know this, we know all these things we have learned in the previous class. So now, using this convex lens, if you project any image on a screen, because it is going to form real and inverted images. So if you are going to project an image using a convex lens on a screen, if you place a screen here, you are going to get the image. At this point, where all the light rays come and meet at this point, if you keep a screen here, that is focal plane, you are going to get the particular image of the object on the screen. Right. So here, the image, if you look at that image, particular image, the image will be very bright. It will be very, very bright. And it will be a full size image. It will be bright and also it will be a full size image. So the images which are got in a convex lens are of full size and they are bright images. So now, if you cover this lens by a black cloth, cover this lens by a black cloth, half of the lens if you cover it by a black cloth. So the black cloth is said to be an opaque object, it won't allow the light rays to pass through it. So therefore we don't get these two light rays after refraction. So the light rays come and fall on this black cloth, but the light rays, that is, they cannot pass through the black cloth and they cannot get refracted. So when you place the screen at this place now, you are going to get the same image, no doubt in that, which is also in full size. But the intensity of the image will decrease. The intensity of the image will decrease, or the brightness of the image will decrease. Why? This was the question asked. It was a very beautiful question asked in the examination. So when a convex lens is half covered by a black cloth, still we can see the image of the object on the screen. How this happens, something like that, the question was there in the examination. So the concept behind this is very simple. When all the light rays passing through the lens fall on the, that is, they get refracted and the image is formed here on the screen, then the image will be very bright and it will be of full size. When the lens is covered, half the lens, exactly half of the lens is covered by some black cloth or an opaque object, then also when we keep a screen here, we can get the image of the object, but the image of the object will be, right, its intensity of the image will be less, but along with that you will get the full image. Only what changes is the intensity of the image. So why this happens? Why the intensity decreased? So intensity, as the intensity of the image as it is decreased. Why it decreased? Because we have reduced the aperture of the lens. That is, we have made the incident light rays falling on the lens, we have reduced it by keeping a black cloth on it. That is, we have covered the aperture of the lens. So we have reduced the percentage of the incident light rays falling on the lens. So therefore, we come to a conclusion here. So what is the conclusion? The intensity of the image falling on the lens, the intensity of the image formed on the screen is always directly proportional to the square of the aperture of the lens. The square of aperture of the lens. So it's very important. So intensity of image formed is always directly proportional to square of aperture of lens. Square of aperture of lens. So in both the cases you get the full image, but when you cover the lens by half of the lens by a black cloth, then also you are going to get a full image, but the intensity of the image decreases. So why it happens? Because the intensity of the image formed is always directly proportional to the square of aperture of the lens. So more the aperture of the lens, more the brightness. More the aperture of the lens, more the brightness in the image or the intensity of the image. Less the aperture of the lens, less the intensity of the image. If you keep this in your mind, you can answer that question. Right? So until now, we have covered all the theoretical parts, all the theory connected to light chapter. So in the next session of light, that is in tomorrow's session, I will be be going with numericals on lenses. Very important and very easy problems. Nothing to worry. So just see this video and the previous video tomorrow once again. Watch it and get ready with the sign conventions which was done in that previous video, which is the third previous video. Look all the 3 videos and sit to look at the tomorrow's video on numericals so that you can understand better. Right? I hope you are studying well at home. Don't waste your time. I am observing that the views of the videos day by day they are decreasing. The reason behind that is you are not watching the videos properly. You are not taking the things very seriously. See, we do not know what the things are going to come in future. Still we do not know when the regular classes are going to start. If you ignore these classes also, I can understand that virtual classes will never replace the real classroom. I know that, I understand that, but at least a person having nothing is getting something. If you're not eating that something also, it will be a big problem in the future for you, because education is everything for a child at this particular age. Without learning concepts, without having knowledge, you cannot do well in your next coming classes. So I hope you will be serious. You are going to look into the videos, right? And you are updated every day, right? So stay home, stay safe, keep learning.